So we talk about weight to volume relationships, starting with the difference between apparent and absolute volume. What is the difference you see here? What's the difference between apparent and absolute volume? What do we see here? This is apparent volume. This is absolute volume. What is the main difference?
Voids.
Voids, exactly. So if you exclude the voids between the aggregates, granular media, and if you had a way to put everything together completely packed, then you had absolute volume. A good analogy is if you compare a bar of chocolate to the same amount of chocolate, let's say in Hershey Kisses. They may be the same amount of chocolate, but one is compact, no voids. Here you have voids in between. You have individual chocolate kisses, the small ones. So kind of you see that the volume is not the same. And which one takes more space is obvious, apparent or absolute? Apparent. Obvious. Okay. So let's start with the first definition. Dry rotted unit weight. So sometimes you see it abbreviated as DRUW. The name is weight, but this is actually a measure of density. Look at the definition. It's the weight of the aggregate, so this is aggregate weight, divided by the apparent volume. So the most important thing to pay attention to is that this is apparent volume. And there is a way according to ASTM C29 to measure it. What does ASTM stand for? What's ASTM?
American Standard. American Society of Testing Materials.
Exactly. American Society of Testing and Materials. How many are taking C337? You should have seen some ASTM, hopefully, right? When you are doing different tests, you learn that this is according to a different standard. And this standard says this is how we measure dry rotted unit weight. You have a bucket, 1/4 of cubic feet. And then you fill it up with aggregates in 3 layers. When you put the 1/3, you use a rod, and 25 times you rod it. So you compact it a little bit. And then the next layer and the next layer. And then you weigh, and you divide the aggregate weight by the apparent volume. How much is the apparent volume here in this test? It is basically the volume of the bucket. It's 1/4 cubic feet. Right? You fill that up. You don't care how much void there is in between the aggregates. Let's do a quick example. So for those of you who are not taking C337, ASTM, again, is American Society for Testing and Materials, and you may recognize this logo. You're going to see it often. That's the ASTM logo. It appears on all the standards, etc. Okay, let's do this example together. Very simple. You can talk to each other. parameter, right? You shouldn't forget that this is parent volume. That's the unit. But is this the real density of the material? No, because depending on how it is compacted, you are going to get a different number, and density is a material property. So to get the density, we actually need to have the absolute volume. So density is, of course, weight or mass divided by the absolute volume. Very related to density, there is another quantity which is called a specific gravity. And that's the density of aggregates, which is this, divided by density of water. It's kind of a relative density. And this parameter, a specific gravity, doesn't have a dimension because you divide two densities by each other. And if you are taking soil mechanics or equivalent, you may have seen it written as G or G sub S. These are all the same things. Okay. Now let's solve this. The same problem as before. Now the absolute volume is given. So first calculate the density. Also a specific gravity, which requires you to remember the density of water, 62.4 pound per cubic feet. So you have to use the same units for density of water as you have for your aggregates. Don't forget to subtract the weight of the bucket. If you work anything in the lab, this is kind of how to measure. You first weigh the bucket, and then you put the aggregates inside, weigh them together, and then you subtract. Now we are dividing by absolute volume, and this is a real density. Which, as you can see, is larger than the dry rodded unit weight. And a specific gravity, you just divide this by the density of water. So specific gravity is sometimes called relative density. It's a material property. And just that you don't forget, we divide it by the density of water, and kind of I've given this here. And aggregates, their specific gravity is typically about 2.5 to 3. Cement, for example, is 3.15. So if you want to compare, 1 cubic feet of water weighs 62.4, aggregate weighs 160, and cement 196, just to have a sense. And everything is absolute volume, so we are not taking into account the voids. Now, when we do concrete mix design, you see tables like this very often. The ingredients of concrete, you will see, are coarse aggregates, which last time we saw it is anything which is retained on sieve number 4. Why everyone is so tired today? What happens? It's because of the weather? Yeah. Yeah. You all look a little bit tired. It's Wednesday. Sand is what passes through sieve number 4. Then we have cement, water, and air. So just to make sure that you are not falling asleep, try to complete this table. So specific gravities are now given for different materials. So Ca again is coarse aggregate, sand is fine aggregate, cement, water, and air. So you want to see we want to see 100 cubic feet of concrete, how much it weighs, and what is the partial weight of each component. Work together, try to come out of the tiredness, whether related or I don't know what related situation. Yeah, it doesn't help that you don't see the sound. It's getting warmer after this, hopefully. So that's a specific gravity. It's not density. If it was density, you would just multiply it by the volume. But this is density divided by density of volume. This is something we do in concrete mix design. So you see, so to get the weight, you need to multiply a specific gravity by the density of water and then the absolute volume for each component, and then sum them up. And this is kind of common way of making these tables, to put the units up there so you don't need to repeat them everywhere. Just check your numbers. Hopefully I haven't made a mistake. Yes, I need to call these guys again. Our screen is still very yellow. Okay. Any questions about this? Everyone copied the numbers? Now, the hard thing is always to find out what the absolute volume is. This is not a very straightforward thing to find out because it's hard to get rid of all those voids. So, if we have the specific gravity and the dry rodded unit weight, then we should be able to calculate absolute volume. So let's try that for this example. So try to work with your neighbors and work on this problem. So we have dry rodded unit weight, 105. Specific gravity is also given. The question is, what's the absolute volume and what's the volume of the void? Units. Don't forget the units. Haven't seen any correct answers to haven't seen any answers. Start with the definition of dry rodded unit weight. So start with the definition of dry rodded unit weight. Calculate its So, first, from the definition of dry rodded unit weight, its weight over apparent volume, which is 0.25, right? So we get the weight, and then you have the specific gravity. So you can get the absolute volume. Write it again. So this is basically the density, which is the density of water times the specific gravity. And the volume of voids is the apparent volume minus absolute volume. Most of you had it right. Okay. This is what I gave as a pop quiz this morning. Okay. So sometimes a specific gravity is defined by just dividing the mass of solid over the mass of water if they have the same volume. So don't be surprised if you see the definition just division of two masses, but they have to have the same volume. And I already told you that you may see different ways of writing a specific gravity, G sub S, you have the same thing. Also, it's useful to know the density of water in other units. So we just talked about the US customary units, but in the units everyone else in the world is using, the density of water is 1,000 kilograms per cubic meter, or 1 gram per milliliter, or 1 gram per cc. So something to know that you will be using later on. Pretty much the same. To measure the specific gravity in the laboratory, we have to find out the absolute volume of the material. And we use a trick, as I will show you. So you put the aggregates inside water, and as I will show you, you will actually measure the weights in water and with water. So don't be surprised to see this other definition where you are just dividing the two masses. This only makes sense if the volumes are the same. Okay. Have you measured a specific gravity in the lab? Yes? So you have done it already. How did you do it? Does anyone remember? No? No one remembers? Is it more like demo or you do it yourself? You do it yourself and you don't have any recollection what happened? Do you remember that you had to at least put the aggregates inside water and measure the buoyant rate and so on, something like that? Okay. Okay. So when we measure a specific gravity in the lab, you need to know the absolute volume for density, and this is hard. In the ideal world, you would know the absolute volume, and you would just divide the mass. So you would just weigh your aggregates, and you would know the absolute volume. So here, for example, 500 over 250, it's a gram per millimeter. Then you would divide it by density of water in gram per milliliter, which is only 1, and you would get a specific gravity. This is in the ideal world. Yeah, but this is, we don't know, what we don't know is the absolute volume. So engineers have figured out a way to do it, which you have done in the lab. And I just want to explain to you how it is, especially if you are not taking the lab. This is how it goes. So you will have a bucket of water of known volume, and also because a specific gravity or density of water is 1, the volume of mass in gram and milliliter, they are the same. So this is how it works. You put the aggregates inside the water, and of course the aggregates would displace the same a volume of water equal to their volume. This you know from physics, right? So their volume was 250. They are going to displace 250 milliliter of water. If you remove that, then you have the same volume that you started with. But now you have water and aggregates together. And you can weigh it. So look at now the masses. We started with 400 grams of water, 500 grams of aggregates. If you put aggregates inside water, you get 900, of course. And we remove 250 and we end up with 650. Now, I can jump ahead. So to get the specific gravity, it turns out that you can see it here actually. Mass in air, 500. If you then have mass in air plus mass of water, and then you subtract mass of aggregates inside water, you are going to get basically the 250 that you were looking for. And that's what you have done in the lab, I'm sure. And probably you followed ASTM and now you forgot about it. But this is why this would work. You can see with the numbers, you can see with the cartoons, so hopefully it makes it clear. I'll show you the ASTM formulas a little bit later, so you see that it's pretty much the same. So you can divide them basically when you have the same volume. Now, so far, the dry rodded unit weight this is The material it's called dry, so it is completely oven dry. It turns out that we have 4 different states of moisture. So starting from left to right, it is oven dry, or bone dry, sometimes it's called. Then you have air dry, saturated surface dry, or SSD, and then you have moist. Now we use W sub S for oven dry, air dry or moist, WM, and then WSSD for weight. So these are weight of the aggregates at different moisture states. Now each one of these cartoons is one aggregate. You see some voids inside, these are impervious. You can't do much about them, forget about them. What's important are those roughness and pores on the outer surface. When it is oven dry, those pores are completely empty. You see it in the picture. If it is air dry, there is a little bit of water there. If it is saturated surface dry, they are completely filled with water. If you have a layer of water, anything more than that saturated surface dry, then it is moist. This is very important. Why? Because depending on the moisture state, if you use the aggregates, let's say in a concrete mix, if they are less than saturated surface dry, they want to first absorb water to become saturated, then the rest of the water is available for workability. I don't know what cook, I'm not a good cook, I cannot make a good cooking example, but it is, let's say, if you are using some sauce and some material, like eggplants maybe, they absorb a lot of sauce. So they take a lot of sauce and there is less sauce available to make your dish, whatever dish that is. I said I'm not a good cook. Now, on the other hand, if you use ingredients which are wet, let's say you start with very wet potatoes. These potatoes are going to give water into the soup. So you need to reduce the amount of water that you plan to put in the soup to get the same consistency. It's exactly the same in concrete. So if you have aggregates which are very wet, that means they are more than saturated surface dry. They are going to release some of that water to the mix. And then if you add a lot of water to it, then your concrete will be too liquid. And this is not what you want. Because if the concrete is too liquid, it won't be as strong as you planned it to be. Does it make sense? That's why this is very important, super important to understand these states and to be able to calculate moisture content and deficiencies, as you will see. So moisture content, the definition is very simple. It's how much moisture you have divided by the dry weight. So you have, this is basically the amount of water, the weight of the moist state minus the weight of the dry state. What is the difference? It's the water in the pores, right? So this is the water. And here is, remember, this is the dry, oven dry. This is easy to get because you just put the aggregates inside the oven, you let them be for several hours, you monitor the weight, and at some point you see that the weight is not changing anymore. That means that they have all the moisture is evaporated. You don't need to worry about it. And that would be your dry weight. So moisture content, the definition is, first of all, it's based on weight, not volume. And it's just the amount of water over oven dry weight. That's important. And if you calculate the moisture content when the material is saturated surface dry, look at the picture. Those pores are completely filled with water. Then this is called absorption. But in terms of what it is, it's just a moisture content. It just has this name, right? It's the moisture content at SSD state. It's the same thing. And you multiply it by 100, so you have in percentage. Any questions about this? Now there are a few other important things to realize here. One is anything which is more than surface saturated dry, it releases water. If the aggregate has less moisture, it absorbs water. So the difference between the moisture content at the other states and the SSD, the absorption, let me write it like this. It's called absorption capacity. This is nothing else but absorption. The difference is called absorption capacity. If you have less moisture than SSD, aggregates want to absorb water. If it is more, they release water. Simple. And you need to account for that in concrete mix design and calculate it. That's why we are learning this here. And we'll start with an example where it makes everything much easier. So this is basically what I was just telling you about. Let's start with an example. So we have a mix of fine aggregates. We know how much. And a mix of coarse aggregates. We have the weight. The fine aggregate has a moisture content of 2% and absorption of 3.4. Coarse aggregate has a moisture content of 1.3% and absorption of 3.8. So the question is how much water you need to bring both aggregates to saturation. And remember one thing, if you are not told, if you just say these aggregates with this moisture content, it means that these are air dry. So I've written it up here. So unless stated, when you get the moisture content, it's the air dry state. So let us start. First, let's start with the fine aggregate. The moisture content is 2%. What is the dry weight? That's where we have to first start. So let's first calculate the weight of the fine aggregates, the oven dry weight. WS. So here is air dry. Here is oven dry. And moisture content is zero. then for the second part, remember that Wm minus Ws is the amount of water. So this is weight of water basically over So when you start, basically, let's say for fine aggregate, to get the oven dry for fine aggregate, basically this is and for coarse aggregate this is the start for fine aggregate, coarse aggregate. Think about how to calculate the added water. I guess we stop here. Bring more energy on Friday. I don't know how.